Physics operates on rules we've spent centuries writing down. We rely on a strict set of equations to explain how objects move and interact. But it turns out, those rules are incomplete. A machine learning model caught an anomaly in recent laboratory data, a pattern that defied the math we normally use to describe reality. This happened inside a vacuum chamber at Emory University, an experiment built to house a highly unpredictable environment known as a dusty plasma. Finding order inside this extreme chaos suggests our current measurements miss specific, subtle interactions. There are forces at play that human observation alone hasn't been able to isolate. Plasma is the fourth state of matter. It happens when gas gets so hot, its electrons break free, creating an electrically conductive soup that makes up about 99% of the visible universe. When charged microscopic grains get mixed into that soup, you get a variation called dusty plasma. It exists all over the cosmos, allowing charged dust to hover above the surface of the moon. It also happens right here on Earth. When heavy soot mixes with smoke inside a raging wildfire, the resulting dusty plasma can scramble the radio signals firefighters rely on. To study this unpredictable state, the Emory team built a controlled simulation. They suspended tiny plastic particles inside a plasma-filled chamber, mimicking those real-world extreme conditions. They tracked the dust using a tomographic laser sheet. As light sweeps the chamber, a camera records snapshots, reconstructing the three-dimensional motion of dozens of individual particles. But the paths didn't make sense. Known formulas failed to predict where the dust was actually going. The physics happening inside that chamber were too complex for our standard equations to capture. The researchers realized that to read the data correctly, they had to step back and let an entirely new type of observer do the looking. The team built a custom neural network from scratch, specifically tailored for physics discovery. Most modern AI models require massive, sprawling datasets to learn anything useful. This team had a different constraint, a small pool of experimental lab data, meaning the network had to be highly efficient to catch on to anything new. To make that work, they structured the network to strictly follow the basic rules of physics, while giving it the freedom to infer the hidden forces we hadn't mapped out yet. The model separated every particle's motion into three distinct layers. It isolated the drag from its velocity, the downward pull of gravity, and the complex forces passing between the particles themselves. By anchoring the AI in basic reality, they stopped it from making wild guesses. That rigid framework paradoxically allowed the model to identify interactions humans had missed entirely. After training on the particle trajectories, the AI mapped the system with over 99% accuracy. In doing so, it confirmed the existence of complex asymmetrical interactions known as non-reciprocal forces. You can think of it like two boats moving across a lake. Each boat creates a wake that affects the other. Depending on exactly where they are positioned, those waves might push one boat forward while pulling the other backward. In the dusty plasma chamber, the AI proved a precise version of this. It showed that a leading particle always attracts the trailing one, while that trailing particle simultaneously repels the leader. This animated chart shows long-standing assumptions that charge increases in a straight line tied to size, and forces weaken uniformly over distance. But the AI revealed complex curves dependent on temperature, proving that particle size actually dictates how fast those forces drop off. The AI's model provided a more accurate description of these forces than the standard formulas found in current physics textbooks. The dynamics captured in this laboratory scale up to the broader study of many body systems in nature. Physicists refer to this broadly as collective motion. It is the exact same dynamic that governs how thousands of individual birds synchronize their flight paths to form massive, shifting flocks. The framework also applies to living systems on a microscopic level, specifically how human cells communicate, interact, and move as a collective unit. Researchers are already looking to apply this specific neural network to oncology. They want to map how interactions between individual cells allow some to break away from a tumor and travel to new locations to become metastatic. The hidden forces steering glowing soot in a wildfire, or dust hovering above the moon, might share the exact same physical framework as the mechanisms behind deadly biological diseases. Neural networks have moved into the realm of active discovery, identifying physical laws that were previously hidden within the data, but it still requires human intuition to carefully design the models and interpret the results. We have to build the exact right cage to capture these novel alien insights. We now have a tool capable of isolating mechanics that were previously invisible to researchers. If an AI can refine our understanding of a system as complex as dusty plasma, what hidden law do you think it will uncover next? Let us know in the comments.